In this lesson, we're going to look at the difference between valence and core electrons. We're going to learn to identify the number of valence electrons in an element and understand how atoms become more stable because of the octet rule. Let's look at an example with aluminum. How many electrons are in a single atom of neutral aluminum? We have an atomic number of 13, which means 13 protons, so we must also have 13 electrons. Next, we're going to arrange our electrons in the different energy levels. So we have 2 in the n equals 1 level, 8 in the n equals 2 level, and 3 in the n equals 3 level. When we look at this, what we see is that these are the core electrons in the n equals 1 and n equals 2 level, and the top electrons in the n equals 3 level are what we call our valence electrons. So the valence electrons are those which are in the highest energy level where there are electrons. Notice I'm talking about the n equals 3 level here. There are no electrons in the n equals 4 level, so that won't be the valence shell. The n equals 3 will be the valence shell. Anything in a lower energy level will always be the core electrons. The reason we're so concerned about the valence electrons is because these are the electrons that are involved in bonding. Whether we're talking about forming molecular compounds or ionic compounds, it's the valence electrons that undergo change and interact with other elements to form bonds. Let's look at some trends in electron arrangements that are going to help us predict the number of valence electrons in many of the elements on the periodic table. Let's start with lithium. In lithium, we have 3 electrons, which means we'll have 2 electrons in the n equals 1 level and 1 electron in the n equals 2 level. When we go to sodium, we have 11 electrons total. We have 2 in the n equals 1, 8 in the n equals 2, and 1 in n equals 3. When we go on to potassium, we have 19 electrons. So we have 2, 8, 8, and 1. Notice that all 3 of these have 1 electron in their highest occupied energy level, and therefore they all have 1 valence electron. When we look at the periodic table, we'll see that lithium, sodium, and potassium are all in the same column of the periodic table. As a result, we know that elements in that first column of the periodic table will all have 1 valence electron. Now, let's look at the second column. We have beryllium with 4 electrons, so we have 2 and 2. Magnesium has 12, so we have 2, 8, and 2. Calcium has 20, so we have 2, 8, 8, and 2. And we see that all 3 of these elements have 2 valence electrons. All 3 of these elements are in the second column of the periodic table. Let's look at one more example on the right side of the periodic table, looking at fluorine, chlorine, and bromine. These are in a group known as the halogens, which are in the second to last column, right next to the noble gases. And we see that we have 9 electrons in fluorine, so we have 2 and 7. We have 17 electrons in chlorine, so 2 and 8, and then 7. And in bromine, we have 35 electrons. Now, bromine is past where we are going to look at determining the electron arrangements. But what we do know is that bromine also has 7 electrons in the n equals 4 shell. What we can see is that all of these elements have 7 valence electrons. So knowing these trends will help us predict the number of valence electron of many of our elements, even if we just know the number of valence electrons in the element at the top of the column. When we look at our noble gases, which are in the last column on the right side of the periodic table, what we see is that these elements are very unreactive. They're much less likely to interact with other atoms to form bonds. And when we look at our electron arrangement for one of them, neon, what we see is that we have 10 electrons. So that means we have 2 electrons and 8 electrons in the two energy levels. And if we did this for all of our noble gases, what we would see is that we have a similar pattern. They have 8 valence electrons. And this is where the octet rule comes into play. So the noble gases have 8 valence electrons, which gives them a great amount of stability, so they don't need to bond in order to get more electrons around them. And when we start looking at when elements form charged species, we're going to see how they gain or lose electrons in order to look more like the noble gases. So if we look at oxygen, it has 8 electrons, so 2 and 6. Fluorine has 2 and 7. Sodium has 11 total with 2, 8, and 1. And magnesium with 2, 8, and 2. And looking at these values, we're going to see that oxygen and fluorine would like to gain 2 and 1 electrons respectively in order to look like neon. Sodium and magnesium will want to lose 1 and 2 electrons in order to look like neon.